Hello YouTube, De-bodgery here. I have in my possession a VESC / Trampa 100-250 controller. This is direct project work by Benjamin Vetter. If you don't know who that is, he is the inventor of VESC. And V in VESC is Vetter. You know, it's that initial. And then ESC is Electronic Speed Controller. So Vetter's Electronic Speed Controller. He invented it. It's, you know, a vast piece of his work, personally, his work. And he made all of it open source. So, you know, all I can say is solid props to Benjamin Vetter, because he could have very easily have kept this all to himself, kind of like what ASI has done, and never shared with anybody. But because he did make it open source, VESC is taking over literally everything else, pretty much. There are a few other new things that are coming out, but if you look at the vast majority of personal electric vehicle controller development, it is majority, by a good margin, all VESC-based stuff. And it's very good, and it's only getting better. So, yeah, solid props to Benjamin. This is super cool. I am so glad that you made it open source, because you made the world a better place as a result. And I wish other companies would think along the same lines, but they don't. Instead, they want to hold everything close to their chest, control everything, you know, like what ASI does. And while I like their controllers, I don't like their company. Whereas Benjamin, yeah, thank you for opening this up to the world. That's about as best I can say there. Yeah, that makes you are a rock star, Benjamin. Yeah. Anyway, this controller design is very simple. As far as the components, there's literally 3 of them. There's this top cover. Well, I guess there's more if you want to count the screws. So you have this little pile of screws right here, and that goes all around the perimeter to make sure that thing is held down really good. And in fact, there's 3 screws right here, because that's where the Mosfets are, to hold them down really good. Yeah, this is a very, very simple design. You don't have like a shell. There's no heatsink here, and you do need one. Yeah, you've got 6 holes that go all the way through everything, so you can bolt this directly down to a heatsink or to a water block or whatever to keep it cool. You don't run these without a heatsink. There's simply not enough mass here in aluminum for you to effectively pull it off for more than very, very low load testing. Otherwise, as soon as you want to use it on something, it's going to overheat, and then it's going to go into thermal limiting just so you don't burn it out. So you absolutely flat out got to put it on something that can pull heat away from it, period. That's just how this works, and that's pretty common for everything that's VESC, or most everything VESC. There's a few, say like the X9000 from EBMX, or the 750 from Tronic. I don't know if there's anything else that's VESC out there that actually has a built-in heatsink. Everything else, you pretty much have to mount it to something. You know, pretty much all the yeah, I'm pretty sure all the Flip Sky stuff, you have to mount it to things. I think that's true for like the FOC. I'm trying to think of one. I can't think of anything other than the Tronic 750, and yeah, I think even like Schul, you have to mount it to something. Anyway, it's a very common thing in VESC that you've got to mount it to a heatsink. So just expect that that's going to happen, and you certainly have that here. So the controller, as you can see, is really, really compact, very power dense. You know, 250 amps, that's not a fake number. You know, it seems impossible in something smaller than my hand, but there it is. Yeah, he's not blowing smoke out of his ass. So these are real values. All right, so let's pull this lid off. Okay, so as you can see, there's no waterproofing here of any kind, so make sure you put this inside a box where it can, in fact, stay out of the weather, because that's the intent. On the back side of this top piece, which is basically just a thick piece of circuit board with no traces on it, there's this little piece of silicone on here, precision piece of silicone. You can see like the little impressions in here, and that presses down on the shunts, and that presses down on the Mosfets. And in fact, you can see those screw holes right there. So those are pressing this silicone rubber piece onto the shunts and pushing those down onto the Mosfets and onto the heat spreader. So that's how you secure the Mosfets to get good thermal transfer. This section over here probably doesn't show up so well, but there's like little impressions on here. That is pressing on the capacitors to hold them secure up against the heat spreader so they cannot move. And there's another little silicone shield inside there. So let's lift the board up. So anyway, yeah, you can see this little silicone piece in here. That's all it does. It's not doing anything. It can't go anywhere. All it is acting as is a little bit of a buffer and an electrical insulator for the large capacitors so that they don't short against the aluminum. Because, well, that would be bad. You know, they are charged after all, you know, when the controller is powered up. This section right here, it's a little bit raised over the rest of the aluminum around it, so that's kind of like your heat spreader for the Mosfets. But really this entire section up here is quite thick. That's really the entire heat spreader, you know, area, if you will, for the Mosfets. And of course, the whole thing is just a solid block of aluminum that has been machined out, and you can of course see the machine marks inside there. So a very simple design, you know, literally, there you go. That's the whole thing. So let's talk about this board for a minute. I have looked up all the part numbers, and when I do the macro video for this, I will talk about them in a little bit more detail. So that's new for my videos, is to actually know what the hell all the parts do, rather than just kind of speculate. But yeah, I will talk about the capacitors in greater detail. So like I don't recognize this name brand KXJ. I'll have to look that up. That's one I haven't done yet. But most likely these are something name brand that I just don't recognize the initials. But everything here is like TI parts or Infineon Mosfets. There's no Chinese parts here anywhere. Everything is, you know, Western name brand parts. You got a Bluetooth module. These are MOSFET drivers, shunts, ceramic caps, extremely short current paths, with copper reinforcing inside the board, very much like what ASI does. So this is a multi-layer board, but you know, here's your battery cable right there. Here's your negative battery connection, and the MOSFETs are right here. I mean, on the other side of the board, they're right there. As far as the battery plus, same thing. You know, that wire is the same length. So here they are, and this trace right here has got gold on it. It's not just copper, and of course there's traces inside the board too, and the vias are underneath the MOSFETs. But again, extremely short current pass. Is enough width there for the tip of my spooger. So 1 centimeter. I mean, it's not very much. 1/4 inch. Yeah, it's really, really small gap right there, and on top of that, there's all the reinforcing inside. So yeah, there is really, really short current pass, and they're reinforced inside. So no great need for more copper reinforcing. Same thing. So right across here, this is your phase buses, and you know, I can see the surface copper that's underneath the silk screening, and then of course there's the vias in there and all that stuff to bring that out to here, which is also got a million little vias inside it, and there's copper tracing inside, so on and so forth. So yeah, these current paths don't need further beefing up with copper because it's built in. So yeah, clever design, good idea, and saved extra manufacturing steps. Can't really complain about that. And also, if you notice right here, yeah, you've got really, really short current paths. So here is, you know, your 3 phases out. You've got current sensors right there. That's what these are. These shunts are. You got a set per phase, and this is really common for VESC, that every single phase will have current sensing. And then right there, and right there, that is your phase bus. So extremely short current paths for everything. You know, from battery minus or battery plus in to phases out, that right there is 1 inch. You know, it's really, really short. So, you know, large current buses, things like that, aren't needed because the distances are so short in here. So yeah, you don't need big giant copper things. And also, it's also built into the board. It's not like it's not there. It's in here anyway. But yeah, the distances are so tiny. Yeah, you don't have to really worry about a lot of stuff like that, because there's just nowhere for the current to go except for, you know, literally from here to here. That's it. You know, really, really short distances. So yeah, the current doesn't have any place to get wasted on. It just goes right from the battery right out to the phase wires. Pretty close. Anyway, what else do I want to talk about on this thing? I'm not sure. Oh yeah, so 3 MOSFETs per phase. So this is, I'm sorry, 6 MOSFETs per phase. This is an 18 FET controller. Here is your standard STM32 F405, which is really, really common to VESC stuff. I don't know that I've ever seen a VESC controller that had something else. You know, it's extremely common STM32 variant to use for this stuff. It's got a math module in it. So it's, doing a lot of functionality, and FOC needs math calculation on the fly. These are current sensors right there. So those little guys tie over to these little guys to be able to tell phase amps for each one of the phases. You've got your DC to DC right here, so you got two little buck controllers, a couple of inverters, or inductors rather, a larger inductor. So I don't know this for a fact because I haven't looked at the schematic recently. I've forgotten. Which you can see all that. If you want, you can go look up the whole entire VESC project on GitHub and see all this stuff, and you see all the schematics. So probably that's 12 volts, and probably one of these is 3.3 volts, and the other one's like 5 volts. Or maybe that is 5 volts, and one of those little ones is 12, and the other one's 3.3. I don't really know. I'd have to, like I said, get to go look at the schematic, but that's you've got 3 DC to DCs right there for that purpose. Okay, I think that's everything I want to show for this video. Everything here is really, really beefy, really strong, very, very tight tolerances, good precision, high quality components, all the battery wires, things like that, like this one here. Look at that. When did you see German-made silicone covered wires before? I mean, you do here, because, well, they didn't skimp, they didn't cut corners, they didn't slide on anything. And we will talk about this more with the macro lens.